Okay, in this chapter, we study the generalized coordinates. The two most important examples for the generalized coordinates are 3D spherical polar coordinate and the cylindrical coordinate system. Until now, we have studied the method of Lagrangian mechanics. We constructed the Lagrangian by writing down the kinetic energy and potential energy in the Cartesian coordinate system and applying the action principle, Hamilton's least action principle. We minimized the action and found that the condition for the minimization of the action was to satisfy the Euler-Lagrange equation that is equivalent to the Newton's second law. In many physical systems, we have some symmetries. For example, if we consider the central force problem, then the potential of the central force is normally the symmetric under rotation about any axis passing through the center of the force. Therefore, it is convenient to make use of the coordinate system that is the spherical polar coordinate system. Another example is the cylindrical coordinate system. If we want to consider the mechanics regarding the magnetic field generated from a current flowing along a straight wire, in that case, the system has rotational symmetry about the axis along that wire. That system can be described in a simple way if we introduce the cylindrical coordinate system whose z-axis along that wire. Therefore, it is very important to study these two generalized coordinate systems. And in this generalized coordinate system, which we call the curvilinear coordinate system. In this curvilinear coordinate system, what we have to do first is modify our approach that are all developed in the Cartesian coordinate system. What we have studied in the Cartesian coordinate system is that the Cartesian coordinate system is fixed. It was not moving, and the origin was fixed in the space. In addition, if I want to describe Cartesian coordinates, that means any vector can be expressed as a linear combination of Cartesian coordinate, Cartesian basis vector, and the coefficients in this linear combination. Coefficient is the Cartesian component of a given vector. In the case of spherical polar coordinates, the position vector in the space can be described in terms of a single term, that is radial vector, and the basis vector for that radial direction is ER hat. And if we want to consider the magnetic field surrounding the wire, current flowing wire, then the position of a field point can be described in terms of linear combination of rho direction, planar radial direction, and z direction. So in addition, the displacement will be containing the remaining dimensions. For example, the dx in the spherical polar coordinates will be a linear combination of ER hat, E theta hat, and E phi hat. And the displacement in the cylindrical coordinates will be a linear combination of E rho, Ez, and E phi hat. All right. Anyway, as far as the potential energy is concerned, for the time being, we are considering only the potential that depends only on the position. So U of x1, x2, and x3 will determine the potential energy completely. Once we have Cartesian component dependence of the potential energy, then we must be able to describe each Cartesian coordinates, x1, x2, and x3 in terms of curvilinear coordinates. For example, x1 can be expressed in terms of r, theta, and phi. x2 can be expressed in terms of r, theta, and phi, and x3 too. All right. So, as far as we know, the complete functional dependence of each Cartesian coordinates in terms of the curvilinear coordinates, then the description of the potential energy in terms of Q1, Q2, Q3 is fine. Next step is the kinetic energy. The Lagrangian, our system, has been described in terms of the Cartesian coordinates. If we apply the Cartesian coordinates, the kinetic energy was written in this form: 1/2 m x1 dot squared, x2 dot squared, and x3 dot squared. The problem is that if we want to make use of the curvilinear coordinate system, what we have to do is to express each time derivative of a Cartesian coordinate in terms of the curvilinear coordinates. Therefore, first we consider expressing the ith Cartesian component's velocity in terms of the curvilinear coordinates. First, xi is here. What I have to do is take the total time derivative of xi. Xi is here. Total time derivative must be a linear combination of partial time derivative if x has explicit time dependence. The next one is we take the partial derivative with respect to the curvilinear coordinate qj, and because this is time derivative, using chain rule, I take the time derivative of this coordinate. And then, in case the Cartesian coordinate is depending on the velocity, then it might be possible to consider the time, the velocity, the partial derivative with respect to the derivative of this velocity of a generalized coordinate. Once is not non-vanishing, then by chain rule, we multiply the double time derivative of that coordinate. However, we are considering a system x, y, z axis that are fixed on the ground, and we do not consider the explicit time dependence of the coordinates. Explicit time dependence of the coordinate should be considered in case we are considering the rotating system or accelerating system or moving system. For the time being, we are not considering that kind of moving system. This contribution vanishes. In addition, because this coordinate is independent velocity, it is just fixed on the ground. The velocity of generalized coordinates dependence does not appear at all, because the two system, the x1, x2, x3 system and q1, q2, q3 system are all fixed to the ground. So that's the reason why we've stated here fixed curvilinear coordinate system. Thus, this first term does not contribute the total time derivative of Cartesian coordinates. As a result, the remaining piece, the only surviving piece is this one. Xi dot is proportional to Qj dot. Qj dot is the velocity of generalized coordinates, and multiplied by the partial derivative of xi with respect to qj and sum over qj, because if we want to describe the a single Cartesian coordinates, in general we need to use all three components of generalized coordinates. Because there are xi dot and the right hand side is proportional to qj dot, there's a linear combinations of qj dot. So if I take the partial derivative of xi dot with respect to the velocity of j's curvilinear coordinates, then the result is this coefficient. The shape is the same. Velocity along the x-axis, xi-axis, and velocity. This velocity means that the coordinates time derivative. The Cartesian to curvilinear should be the same as just like the directional cosine in case qj has the length dimension. All right, in summary, this is a quite important result. Later we will use this result frequently. All right, so in summary, what we are considering in this chapter will be two curvilinear coordinate systems. The first one, this one is the beginning point, two-dimensional polar coordinate, and the two most important coordinate systems are three-dimensional spherical polar coordinate system of r, theta, and phi, and the three-dimensional cylindrical coordinate system with the coordinates rho, phi, and z. In two-dimensional polar coordinates, Cartesian coordinates x and y, that are x1 and x2, are r cosine theta and r sine theta. And actually the two-dimensional polar angle theta is actually the azimuthal angle in the spherical polar coordinate system and the cylindrical polar coordinate system. So this the theta runs from 0 to 2 pi. This phi runs from 0 to 2 pi. And this phi also runs from 0 to 2 pi. Because what we have derived that the velocity in the Cartesian coordinate, ith component of the Cartesian coordinate will be the sum of qj dots with a weighting factor of around xi over around qj summed, where j is summed over. In that case, So as is written here, this one contributes, and we need all three terms for a single component of Cartesian coordinate. Okay, and if we make use of the spherical polar coordinates, then the first Cartesian coordinate will be r sine theta cosine phi. Second Cartesian coordinate will be r sine theta sine phi. And third one will be r cosine theta. And the third one is a cylindrical coordinate system. The x1 will be rho cosine phi, and rho is the planar radius. This rho is the square root x1 squared plus x2 squared. Okay. And x2 is rho sine phi, and x3 equals to z. Because we have this kind of vector, when we re-express the ith component of Cartesian velocity in terms of the curvilinear coordinate system, we need to sum over j for the velocity of the coordinate multiplied by this weighting vector. This weighting vector are obtained as follows. x1 r cosine theta, q1, here we have q1 equal r, q2 equals theta. So these factors are all computed in here. R cosine theta x1, so derivative with respect to r is cosine theta, and derivative of x2 with respect to r is sine theta, and derivative of x1 with respect to cosine is r sine minus r sine theta, and the derivative of x2 with respect to theta is r cosine theta. In a similar manner, we can compute the nine terms for x1. If I x1, x2, and x3, if I take the partial derivative with respect to r, what we have is just remove this r vector and copy the sine, cosine phi, sine theta, sine phi, and cosine. And next one, x1, x2, x3, differentiated with respect to theta, r cosine, cosine phi, r cosine, sine phi, and then minus r sine phi, sine theta. And we also compute the phi dependence. So partial derivative of x1, x2, and x3 with respect to phi will be phi minus r sine theta sine phi, r sine theta cosine phi, and it's independent of phi, so it's 0. Next one is for the cylindrical coordinate system. x1 rho cosine, x2 rho sine, and x3 equals z. If we consider this one, x1's partial derivative with respect to rho is cosine phi. In the case of x2, it's sine phi, and third one is vanishing. Next, we take the derivative with respect to phi. The two contributions of phi, cosine because minus sine, so minus rho sine, and this is rho cosine, and this one vanishes. The third, z is independent of x1 and x2, so it is vanishing, and derivative of x3 with respect to z equals 1. So if we write down the kinetic energy, the kinetic energy is 1/2 mxi dot squared in the Cartesian coordinates. Because xi dot is expressed in such a way, so kinetic energy in the generalized coordinates will be 1/2 m qj dot round qj round xi, and I need to multiply one more piece. This xi should be the same, but this is dummy variable, so dummy index must be different. So let me put k instead of j. If I rewrite this, it is 1/2 m qj dot qk dot so this vector is necessary to compute the kinetic energy. Okay? Let us compute the kinetic energy in the two-dimensional polar coordinate system. So, just like what we have obtained, the kinetic energy expressed in the curvilinear coordinate system is expressed 1/2 m qj dot qk dot, and sum over I, the derivative of xi with respect to qj, derivative of xi with respect to qk, and summed over j and k. So j, in the case of 2D polar coordinates, j is 1, 2, k is 1, 2, and I is 1, 2. So 2 times 2 times 2, 8 terms should be considered. For example, if I consider I equals 1, and let me first choose j and k are 1, 2, and 2, 1. J and q are 1, 2, and q1. This is 1 and 2, and this is 2 and 1. And q1 equals r, q2 equals theta, and q2 equals theta, q1 equals r. We know that x equals r cosine theta and y equals r sine theta. So using this, we have r dot theta dot this derivative. Wait a second. Where is it? Okay. So these two are the same, so I multiply 2 in front of the first term and remove this. And then take the derivative with respect to r. We obtain cosine here. And then theta derivative, theta minus r sine theta here. This is what we obtained. So we have just finished the calculation for I equals 1, j equals 1, 2, and 2, 1. That means 2 cases only. Next, we consider I equals 1, j, k equals 1, 1. That means 1, 1, and 2, 2. I equals 1, this we have xx, xx. jk is 2, 2, 1, 1, then 1, 1, 1, 1. Okay, r dot twice, and derivative of r, derivative of r. And 2, 2 case is theta dot, derivative with respect to theta, and same thing. This r dot squared and theta dot square appears, and the derivative, this round x over r, should be a cosine, and that appears twice. I have cosine squared. And then derivative of x with respect to theta is minus sine r sine theta, minus r sine theta. It is squared, so we have r squared sine squared theta. So we have finished it. 1, 2, 3, 4 cases. We still need to compute the 4 more cases. So I equals 2, jk equals 1, 2, 2, 1, just like this. This is the same. 2 times r dot theta dot. And now this one is replaced with the y. X is replaced with y. So y is r sine theta. So derivative with respect to r is sine theta. With respect to theta is r cosine theta. That's fine. All right. And then this is 1, 2, 2, 1. And this is 1, 1, 2, 2. jk equals 1, 1. So r dot squared and partial derivative with respect to r twice. And this is the 2, 2 case, that is theta dot squared and the theta derivative. R derivative for this y is a sine. So we have r dot squared sine squared theta. And theta derivative is r cosine theta. So we have theta dot squared r squared cosine squared theta. So these are 4 contributions and 2 contributions. Let us add these 8 contributions all together to find out the kinetic energy in the 2-dimensional polar coordinates. If I sum the 8 pieces all together, we find that first I have r squared contribution first. 1/2 m r dot squared. I have cosine squared and r squared sine squared here. And then r squared sine squared theta sine r squared sine squared theta r squared theta dot squared cosine squared sine squared cosine squared. Okay, so these 4 pieces are added up, and we have these 2 contributions still to be added. This one has a negative sign, except that everything will be the same. 2r dot theta dot cosine sine and 2r dot theta dot cosine sine with negative sign, positive sign. So they cancel. Because of the Pythagorean theorem, this one equals 1, this one is equal to 1. So final result is 1/2 m r dot squared plus r squared theta dot squared. If you look into this result very carefully, then this one is actually 1/2 m h1 squared q1 dot squared plus h2 squared q2 dot squared. Okay, where h1 is scale vector for radius r. That is what? h2 is the scale vector for the angle theta. That is r. Therefore, this r scale vector is a 1 square, and the scale vector r square and coordinate square. The reason is that the displacement, infinitesimal displacement dx in the curvilinear coordinate system is described in terms of unit vector and its differential along that coordinate. Unit vector e theta hat with the displacement along that coordinate, that is r d theta, this arc length. And if I take the time derivative, this is just to replace dr with the r dot. The dr over dt equals r dot, right? d theta over dt equals the theta dot, right? Because of that, we have r dot and r theta dot as the radial component and angular component. Because this ER and E theta are perpendicular to each other, and ER equals ER squared is 1 and E theta squared is 1. Therefore, the velocity squared is R dot squared plus R squared theta dot squared. Next, we consider this. The computation of the kinetic energy and the computation of the Lagrangian in the curvilinear coordinate system should involve this kind of calculation. We need to transform the result coming from the Cartesian coordinates to the curvilinear coordinate system. First, let us take it to account. Let us consider the partial derivative. This, in case we have q is replaced with x, then it is just like directional cosine. The angle between that cosine angle between two coordinates. But this is generalized coordinates. In case it is an angle, there's a scale factor difference. All right. If I take the total time derivative, just like what we have already studied, these two vanishes. Because this one is independent of time and independent of velocity. All right. And the only contribution is a qk dot contribution. And qk dot contribution has a partial derivative with respect to qk. So we have qj, qk, double derivative. The reason for neglecting this, the last term, is because these two derivatives are commutative. If I move this round t inside, the coordinates that partial time derivative appears. That is vanishing because we are considering the fixed coordinate system. And next one, the first contribution disappears because, again, this derivative moves inside because they are commutative as long as the function is differentiable. The velocity dependence does not appear in the coordinates, so therefore it is vanishing. So final result for this one is qk dot and the double derivative with respect to jk, qj and qk for the ith Cartesian coordinates. Next, we consider the total time derivative of xi. Take the partial derivative with respect to qj. Again, xi dot is expressed in terms of this, and the time dependence, velocity dependence disappears because this is a fixed coordinate. So we have qk dot here. So qk dot here, and we have derivative of xi with respect to qk, and then very outside we take another partial derivative with respect to qj. As a result, if we take the derivative, this is coordinate. It is a time derivative of coordinate, so this one vanishes, and this one can be pulled out of the derivative, and qk dot is placed here, and qj go inside to find out this vector. And because this one is vanishing, we have qk dot and this vector. And actually these two are the same. In the long run, we have found that the total time derivative of this one is the same as the partial derivative of qj with respect to qj for the total time derivative of xi. And actually, this is the fact that this the total time derivative, this one, and the partial derivative with respect to qj, they commute. If they commute, if I put this one to xi, then xi dot means the total xi dot is equal to total time derivative of xi. Okay. Alright, so now we have found that this one, this total time derivative moves into, because the partial derivative with respect to qk, that they commute, so I can put this total derivative to xi to find that xi dot. And okay, this one will be useful when we rewrite the Lagrangian. First, we write down the Lagrangian in the Cartesian coordinates, and then we transform that expression in terms of the curvilinear coordinate system. Now, let us consider this. We have found that in the two-dimensional polar coordinate system, this kinetic energy was written in a simple form, 1/2 m r dot square plus r square theta dot square. Okay, although it looks very complicated. In order to carry out the similar calculation for the spherical polar coordinate system and the cylindrical coordinate system, we had better to study the following things. First, spherical polar coordinate system, we have the first generalized coordinate, curvilinear coordinates, q1 is r. And next coordinate q2 equals theta. And third coordinate q3 is phi. And first we need to re-express the Cartesian coordinates in terms of these curvilinear coordinates. First, x1 is r sine theta. We remember this is x projection angle theta, and this is x3 equals, this is r cosine theta, and the projection onto the xy plane, this one is r sine theta, and this is a modal angle phi. In that case, this is x1 equal r sine theta cosine phi. This is x2 r sine theta sine phi. Okay, therefore in summary we have x1 equals r sine theta cosine phi, x2 equals r sine theta sine phi, and x3 equals r cosine theta. The scale factor for the variable x1, the radius r. This r has the dimension of length, so scale factor for r is 1. So hr is 1. The scale factor for angle theta is r. If I rotate about this angle, this arc length, if this is theta, this arc length is r d theta along the e theta hat. If I shift the position by varying the radius only, then I would get this direction, that is e r hat dr. Here we find that h r equals 1. This is distance. And this distance I have a radius r, so r d theta. So this is r equals h theta. The third one, we have azimuthal angle. If I increase the angle phi, then I have a displacement of radius r sine theta, and then the angle d phi. Okay, so the arc length, this arc length is r sine theta d phi with the direction of e phi hat. We remember that e r squared, e theta squared, and e phi squared are all 0, and er, e theta, er, e phi, and e theta, e phi scalar product are all 0. In addition, these three vectors are cyclic, so cyclic unit vectors, er hat, the triple scalar product of these cyclic unit vectors, er hat cross the e theta hat dot e phi hat is just 1. Finally, the determinant of this matrix. Here, x1 r derivative, sine theta, cosine phi, x2 r derivative, sine theta, sine phi, x3 r derivative, cosine theta, and x1 theta derivative, r cosine theta. Here, c theta is a cosine theta, c phi, or cosine phi, something like that. Okay, x1 theta, r sine theta, cosine phi, x2 r cosine theta, sine phi, minus r sine theta, and finally, with respect to phi, r sine theta minus sine phi, r sine theta cosine phi, and the third one is vanishing. Therefore, the determinant of this one is Jacobian, and actually we prove that this one is the vector for er hat. This is hr er hat, so x1, x2, x3 components, and this is h theta e theta hat for the x1, x2, x3 component, and this is h phi e phi hat x y z component. Therefore, determinant of this, that is defined to be the Jacobian, should be the product of the scale factors. These are three scale factors, HR, H theta, and H phi, and then triple scalar product of these three unit vectors. But we know HR equals 1, H theta equals R, H phi equals R sine theta. Therefore, the product is R squared sine theta, and then triple scalar product is because of it. This is just 1. Alright, therefore, this is like that, and the displacement will be the sum of these independent displacement with respect to the R theta phi direction. This is ER hat dr, E theta hat R d theta, and E phi hat R sine theta d phi. Alright. And next we consider the cylindrical coordinate system. And a cylindrical coordinate system is consists of the three pieces: rho, phi, and z. And cylindrical coordinates is, this is rho, and x1, x2, x3. This is phi. So x1 is equal to rho cosine phi, x2 is rho sine phi, and x3 equals z. So rho cosine phi, rho sine phi, and z are the expression for the three Cartesian coordinates in terms of the cylindrical coordinates. Okay. Again, this column represent the Cartesian coordinates, 1, 2, 3 coordinates of H, rho, E, rho hat, and this one gives H phi, E phi hat, and this one gives H z, E z hat. And computation of partial derivatives will give this rho derivative cosine, rho derivative sine, and rho derivative vanishes. And phi derivative minus rho sine and rho cosine vanishes. Z derivative 0, 0, 1. Okay. And this value is actually, if we compute this is a rho cosine squared phi plus sine squared phi equals rho. We know the answer. However, if we make use of this fact, then if I insert this is a product of H rho, H phi, and Hg, and triple scalar product of E rho, E phi, and Ez hat. Alright. Therefore, this one is a unity, and all these vectors, H rho equals 1, H phi equals rho, and Hz equals 1 can be substituted here. All three product of these three numbers will be rho. And so the Jacobian is rho. In addition, displacement can be written in the form dx along the rho phi z direction with the scale factor d rho, scale factor d phi, scale factor dz. And this h rho is 1, h phi is rho, hz equals 1. Therefore, displacement, the infinitesimal displacement is written in this form. If I do the calculation for divide this one by dt, then it becomes velocity. and rho direction velocity rho dot, phi direction velocity is a rho phi dot, and z direction velocity will be z dot. In a similar manner, if I square all three things, because they are all perpendicular to each other and they are normalized, the velocity squares in the cylindrical coordinate system is rho dot squared, phi dot squared, and z dot squared. Let's take a rest. Okay, we are on the way to describe the mechanical system in terms of the generalized coordinates, especially the curvilinear coordinates. We focus on two curvilinear coordinates that are cylindrical coordinate system and the spherical polar coordinate system. In order to describe a system, we need to know the Lagrangian. But in order to make use of the generalized coordinates, curvilinear coordinates, we have to express the kinetic energy and the potential energy in terms of the generalized coordinates. First of all, we were able to describe the potential energy, which is a function of x. In the Cartesian coordinate system, it is a function of x1, x2, and x3. And for example, if we make use of the cylindrical coordinate system, we have x equals rho cosine phi, y equals rho sine phi, and z equals z. So this is x1 and x2 and x3. And we can substitute this one in here, this one in here, this one in here. So finally, the potential energy was written in rho cosine phi, rho sine phi, and z. So the potential energy was successfully described in terms of these curvilinear coordinates. The next step is to describe re-express the kinetic energy of the system in terms of the curvilinear coordinates. The simplest way to describe the curvilinear coordinates was this one. And actually, this kinetic energy in general is 1/2 mv squared, and it was this x dot squared can be described in terms of the Cartesian coordinates as a Cartesian coordinate velocity squared summed over I. That means x1 dot squared, x2 dot squared, x3 dot squared, and add them up. We recall that each xi that can be described by qj dot qj xi. Okay, if I substitute this one in here, but because this is a dummy index, we must use a different one for different vector. So one xi dot uses jj, and the other xi has different index kk here. Anyway, in 3 dimensions, this is a sum over I, sum over j, and sum over k, and every index ijk runs from 1 to 3, so we have 3 times 3 times 3, 27 terms in this expansion. At the end of the day, we were able to find this whole contribution is simply expressed in this way. We could have expanded this 27 pieces in detail, but as we remember, even in 2-dimensional polar coordinate, this calculation is quite involved. Instead, we make use of the fact that displacement can be re-expressed in terms of basis vectors of the curvilinear coordinates. If we make use of this fact, then in the cylindrical coordinate system, the displacement, infinitesimal displacement, will be a linear combination of three basis vectors. So rho direction, phi direction, and z direction. And the displacement along that direction is the rho for the planar radius rho. And actually, this one we have multiplied 1. This one is the scale factor. The reason why the scale factor 1 is that rho has the dimension of length. So, as far as phi is concerned, the angle phi has the displacement only if we multiply the scale factor rho. So rho d phi is the displacement along the direction of phi. And again, z has the dimension of length. Its scale factor is 1. Therefore, the infinitesimal displacement is written in this form. If we want to compute the velocity, we could have used this complicated formula, but if we make use of this basis, it is quite simple to express this. So dt will be divided, so d rho will be replaced with rho dot. Rho dot is d rho over dt. And this velocity becomes a phi direction velocity, becomes a rho phi dot. And z direction velocity is a z dot. The velocity squared is the sum of these three components by making use of the Pythagoras theorem. Because all three unit vectors are normalized to be unity, and all three vectors are perpendicular, and they are cyclic. We make use of the Pythagoras theorem to find that velocity squared is rho dot squared plus rho squared phi dot squared plus z dot squared. In other words, in general, it is h1 squared q1 dot squared plus h2 squared q2 dot squared plus h3 squared q3 dot squared. In any kind of curvilinear coordinates whose basis vector q1 hat, q2 hat, q3 hat are all normalized to be 1 and they are perpendicular. In a similar manner, we can compute the displacement in the as a result, the velocity squared is written in this form. So the kinetic energy in the cylindrical coordinate system is written like that. If we consider a spherical coordinate system, the displacement is decomposed into r direction, theta, and phi. And we recall that hr is 1, h theta equals r, and h phi equals r sine theta. Thus the displacement is along the r direction, dr, along the theta direction, r d theta, and along the phi direction, r sine theta d phi. If I take the derivative with respect to time, so this is dx over dt, total time derivative, then what we have is just to replace these differentials with the dots. So this one becomes r dot, and this one becomes r theta dot, and this one becomes r sine theta phi dot. Does the square, and we also have this unit normalization condition, and all three vectors are orthogonal. By applying the Pythagorean theorem, velocity squared will be r squared, r dot squared, r squared theta dot squared, and r squared sine squared phi dot squared. If we substitute this one into the kinetic energy, 1/2 mv squared, what we have is this. Now, we are ready to attack the problem. Now, L is expressed in terms of Q, I, dot, and Q, I, and possibility. What happens to the variation of L, variation of S, and what is the equation of motion? Then we shall find that the equation of motion in the curvilinear coordinate system is exactly the same as those appearing in the Cartesian coordinate system, except that xi is replaced by the qi's. But is it really right? We shall prove this. First, we consider the variation. Variation involves the variation of the path. Physical path, from the physical path to the unphysical path, variation is called the delta xi for the Cartesian coordinate system. The Cartesian coordinate system variation should always be expressed in terms of, because xi is a function of q1, q2, and q3, we make use of chain rule to find that this can be varied along the direction of qk and multiplied by qk's variation and sum over three components, because xi may not be along a single direction of cube. So each xi is I is 1, 2, 3, they may have overlap with the q1, q2, q3 all together. And then variation of the Cartesian velocity is actually the same as the variation of the Cartesian coordinate, and then take the total time derivative. Again, we substitute this relation into here to find that this variation of the Cartesian velocity is the time derivative of this. All right, so let us consider the variation of Lagrangian. And we will find that this variation of Lagrangian can be expressed in terms of variation by a variation of curvilinear coordinates and the time derivative of curvilinear coordinates. Let's see here. First, we begin with the variation in the Cartesian coordinate system. We recall that this is x derivative and x dot derivative multiplied by x variation, x dot variation. And x dot variation is x variation's time derivative. Consider the first term. First term has this factor, and we just have considered this. This one can be replaced with the linear combination of qk variation, and the overlapping factor is around xi over around qk. This one is actually the Lagrangian's xi derivative, and we find that in the Cartesian coordinate system, Lagrangian has a kinetic energy minus potential energy in any coordinate system, but the kinetic energy in the Cartesian coordinate system does not have explicit coordinate dependence. It has just xi dot dependence, so this one disappears. And the only remaining piece is a u, potential energy. So minus potential energy is So the minus gradient, this is force, right? And then this vector, we have xi, xi. And u is a function of x only. And we do not consider the velocity dependent potential. So this one vanishes. And we do not consider the case in which explicit time dependence exists. Okay, so if this is chain rule, that should be combined together, and this is the derivative of qk. All right, this piece. And second term, this second term can be considered in here. The second term, Lagrangian is substituted, t minus u is substituted into the Lagrangian and velocity derivative, and we rewrite this total time derivative of the variation of Cartesian coordinate. Here, I do not consider the velocity dependent potential, so it is removed. I only have kinetic energy. So kinetic energy, derivative of velocity. And then this delta xi is replaced with this one. So I have this. If I combine these two terms here, substitute here, this one is copied in here, and this term is copied in here. Right? We remember. This one can be combined into two pieces. Time derivative of this, we just before we derived, we found with this dt and qk commutative. So insert the dt inside, then means xi becomes xi dot. Okay, and leaving the delta qk unchanged. And then if I pass this vector, then it approaches here, it becomes a qk dot, delta qk dot. All right, and this one and this one will be multiplied. You will find that this one is xi dot in the denominator and xi dot in the numerator, and derivative with respect to qk. And next one, this is a qk dependent term, and we have also qk dependent term. Just copy this one in here. So this one is in here. Therefore, qk dependent term is this. And then remaining piece is this one. This one is copied to here. We have kinetic energy, xi dot, and xi over qk, and delta qk dot. First of all, these will be combined. Xi dot, this chain rule. So this is just single q derivative. So t minus u's this Lagrangian's qk derivative. And then here we have this one, xi qk. However, we derived this formula previously. Xi qk is the same as identical to xi dot qk dot derivative. So in this term, I replace this one. I just put this dot here. So here dot appears. Again, this kinetic energy is a function of x dot only. So this one will be combined. The chain, according to chain rule, this is just round t over qk dot. Right? Therefore, this step is, this one is this, and xi xi qk, but xi qk was xi dot qk dot, because this one and this one is the same. And we made use of chain rule, combine this to find out this qk dot derivative of potential. Oh, okay. But we remember potential qk dot derivative is also 0. So I can add this one, subtract this one, so that it becomes a t minus u. Okay, so that vector has a delta q k dot over coefficient. This one is Lagrangian, so it becomes Lagrangian, and this one is Lagrangian. So finally, we end up with this expression. This delta L, originally expressed in the Cartesian coordinate system, eventually were simplified into this form. It's variation of Lagrangian was expressed as the partial derivative of qk multiplied by the variation of qk, sum over k, and then partial derivative of Lagrangian with respect to qk dot multiplied by qk dot variation. So we have proved that the variation of the Lagrangian is expressed in the Cartesian coordinate system explicitly. Again, by transforming this one, expressing this xk and x dot k in terms of qk's, we were able to find that variation of the Lagrangian has exactly the same structure, except that the x is replaced with q. Now, we have the Lagrangian and the variation of the Lagrangian, originally made in the Cartesian coordinates, were recombination gave us this kind of result. What happens to our case? Actually, it is the same. We have proved that this is true, and this one is copied, and rounded over qi dot multiplied by delta qi dot, just like the case of Cartesian coordinate derivative. This is just time derivative of variation of qi. Therefore, I can move this derivative outside to take the derivative product of this, and then we need to subtract the piece this piece. So if it is applied to the front fact, minus time derivative of Lagrangian partially differentiated with respect to qi dot and variation of qi. If we combine delta qi dependent terms together, we have this one multiplied by dqi. And next piece is total time derivative of round L over round qi dot multiplied by the variation. So this curvilinear coordinate system version and the Cartesian coordinate system version is identical to each other, except that coordinates are replaced with the counterparts. Now let us continue to apply the least action principle. Least action principle is minimized. If we minimize the action, then the condition is achieved only when it satisfies the Euler-Lagrange equation. And that is the equation of motion. And that equation of motion describes the physical path of the system. Now substitute the curvilinear version of the variation of the Lagrangian into this formula. We find that the first piece is this, and second piece is integrated out because it is a total derivative. If we take integrate this time out, then we have rounded over qi dot multiplied by the variation qi at t equals 2 and minus that value at t evaluated at t equals 1. We know that the variation of the endpoints does not change even in the Cartesian coordinates and as well as the generalized coordinates. So even in the curvilinear coordinate system, variation at the endpoints must be 0, and this will disappear. And we allow the variation for every coordinate independently. In order to satisfy this identity equals 0, the coefficient of each variation of the coordinate must vanish. So finally, we end up with the Euler-Lagrange equation in the curvilinear coordinate system. That's it.